it's really important to bring the power of machine learning to all kinds of different users, both internally and now externally.
Ladies and gentlemen, please welcome back Director, Product Management, Google, Greg DiMichele.
Good morning. Welcome back to day 2 of GCP Next. Thank you all for coming back. I hope you had a good day yesterday. I hope you had fun at the After Dark party. Did folks make that? Good, good. I hope you get time or have had time today to experience the playground that's out there. My 2 favorite ones are the Emoto booth, where you can experience the Vision API in a first-hand way, get your picture taken, see if you can trick it on what emotions you're feeling. And then Query It, the game where you actually can compete with somebody else and then to see what you know about Reddit or Wikipedia or a whole bunch of huge data sources with BigQuery. I hope you also got time to look at the various partners that are out there showing off solutions or add-ons or other software that works with Google Cloud. You know, and it's really valuable to me and rewarding to see so many of you talking with each other, to see customers giving sessions, to see partners giving sessions, and sharing your own experiences. There's also one thing, I hope you'll do me a favor. You know, those of us who are lucky enough to be on stage at events like this are just the most visible part of many, many, many people's work. Whether it's the people who build the demos that you saw, people who build the products, the sessions, the staging and the event people who transformed an empty shell of a building into this amazing venue, our wonderful creative partners at Instrument who helped come up with this amazing lighting design you have. Would you join me in thanking them before we dive into all that? Thank you, they really are remarkable. Today is going to be a little bit of different. Today we're going to give you deep dives into 3 critical technology areas. You're going to hear from the engineering leaders at Google who are closest to these technologies, who've been working to really build out what we think of as Google and Google Cloud. There's no marketing today, you're hearing directly from engineers. We picked these topics because we think they're the ones that are most critical in the evolution of cloud over the next, not just year, but the next several years. And frankly, because we're nerds at heart and we think the stuff's pretty cool. Our first speaker is Joe Cava. Joe runs all data center operations at Google. And you know, they're actually kind of a legendary team within Google because we depend upon what they do to an incredible degree. And it's so easy to take for granted the amazing innovations. So to give us a look inside of Google data centers, how we build them, how we operate them, and the kind of innovation we do, would you please join me in welcoming to the stage Joe Cava. Joe?
Thank you very much. Thanks, Greg. Good morning, everyone. My name is Joe Cava, and I'm responsible for the teams that design, build, and operate Google's data centers worldwide. So today I'd like to share with you a little bit about our culture and our guiding principles. Really, what is the secret sauce that makes Google data centers so unique? So first, imagine your data center. Whether it's a private enterprise data center or a multi-tenant co-location facility. But now, you don't have to imagine anymore. Because with Google Cloud Platform, your data center is Google's data centers. GCP gives you access to high-performance computing available around the world in our highly secure and ultra-reliable data centers. So let me delve a little bit into what makes Google Data Center so special, why we're unique. First, the core principles of our data center program are availability, security, and performance. You know, at the core of our program is our commitment to availability. I've been doing this a long time, and I have evaluated literally dozens, if not hundreds, of data centers all over the world, both public and private. And I can tell you, without a doubt, they are not all created equally. First, when we say 7 by 24, we absolutely mean it. Our designs are fault-tolerant and hardened against failure. Our critical infrastructure is concurrently maintainable. This means that when something does break, or when maintenance is required, we can do that without taking down any part of our critical infrastructure. This makes it invisible to you. Next, we design our data centers with an eye towards the future. So we're always building in hooks into our designs that allow us to upgrade our systems and our network so that we can always keep ahead and keep current with the latest platform's developments. And lastly, we staff our data centers 24/7 with Googlers, our own team of Googlers, that have been intimately involved from design to construction, commissioning of the systems, and operations of the data centers. So second, security. This is truly of utmost importance in the Google Data Center program. Google's focus on security is among our primary design criteria. Our physical security model features layered security that includes things like custom design access cards, alarms, vehicle access barriers, metal detectors, perimeter fencing, biometrics, and even laser intrusion detection guarding the data center floor. Our data centers are monitored 24/7 by high-resolution cameras, internal and external. They can detect and track any intruders. And our data centers are constantly patrolled by our security teams that have undergone rigorous background investigations and training. And as you get closer to the data center floor and to our core network, the security increases. Access to the data center floor is only available through a secure corridor that implements multi-factor authentication, so you need an authorized badge and biometric clearance to get onto the data center floor. And only approved employees that have a business need to be there ever get access to the data center floor or our core network. In fact, less than 1% of all Googlers ever set foot on a data center at Google. We employ a very strict end-to-end chain of custody for our storage systems. From the first time a hard drive goes into a machine until it is verified as clean, erased, or destroyed, we know every movement of that hard drive. We know who, the person, when, the timestamps. We know what, the serial number and the state of the media, and why, its next expected action. And information security and physical security go hand in hand in our data centers. You know, data is most vulnerable when it's traveling across the internet or within networks. And for this reason, securing data in transit is a high priority to Google. Data traveling between a customer's device and a Google data center is encrypted using HTTPS TLS. And as a matter of fact, Google was the first major cloud provider to make this default by standard. And our last guiding principle is performance. You know, we've been leaders in developing ultra-high performance compute systems since the earliest days at Google. Our high performance computing is the result of optimizing throughout the entire stack. Nearly all of our infrastructure is custom designed and purpose-built for our computing needs. From our own dedicated high-voltage subsystems on site to the electrical distribution systems and our cooling systems, they're all working in conjunction to provide the highest level of performance and the lowest total cost of ownership. When I first joined Google, I was kind of amazed at the extraordinary lengths that the company goes to develop our own computing systems. And of course, over time, I learned why. But at the time, it wasn't so intuitive to me. Why do we build our own servers? Why not just buy? Well, we go through all of this extraordinary effort to create our own because, frankly, what we needed at our scale didn't exist when we started. To achieve the performance, efficiency, and price targets that were necessary, we had to build our own servers. We had to invent hardware. We had to develop the software. We had to create a culture for scale and reliability. Google servers don't include any unnecessary components such as video cards, chipsets, or peripheral devices, which can introduce vulnerabilities. Our production servers run a custom-designed operating system based on a stripped-down and hardened version of Linux. And Google's IP data network consists of our own fiber, public fiber, and undersea cables. This allows us to deliver highly available, low-latency services across the globe. But it also means that we can respond faster to demand and provide the capacity you need. From my earliest days at Google, our data center program has been as much committed to our culture as it has been to our principles. The key tenets of our culture are ownership, sustainability, and innovation. We have Googlers that operate our data centers. You see, the norm in the industry is for the design-build contractor to hand over a set of drawings and a set of owner's manuals and the keys to the front door and wish the data center operator good luck. Well, and all too often, frankly, those operations teams, they aren't even employed by the owner. They're outsourced to the lowest cost bidder. And if there's one certainty in data center operations, it's that problems and faults are going to happen in the middle of the night, typically on Sundays, when no one else is available to help out. So we take a different approach. Firstly, we hire the best and the brightest engineers and operations professionals that come from diverse backgrounds, but they all have one common trait. They are systems thinkers. Many of our team members come from mission-critical environments, like the Navy nuclear submarine program, where mistakes can be catastrophic. They understand how systems interact and how they work together. Further, we've built regional teams at all of our data center campuses that are comprised of the engineers responsible for design and construction, working side by side with the operations teams. The experience and qualifications of our staff is unparalleled. The majority of our staff hold advanced degrees. They have professional licenses. They are published in technical papers and in books. They hold patents relative to our industry. And together, these integrated teams are responsible for building the capacity, commissioning the systems, and operating these data centers 7/24. This gives us an unparalleled level of ownership end-to-end of our infrastructure. But for these teams to truly be successful, they need to have advanced real-time visibility into the status and the functionality of our infrastructure. As you know, to say that Google is obsessed with data might be a little bit of an understatement. So to aid our teams, we've built world-class monitoring and control systems for all the functional areas, from the servers and storage and networking systems to our electrical distribution systems and the security systems. We are monitoring all aspects of performance and operations, truly from chip to chiller. But equally important to our culture of ownership and transparency, equally important to our culture of ownership is transparency and continual learning. So when issues do occur, we learn from them, and we can share the learning with all of our teams around the world. We studied the root cause of failures in the industry based on published data. And on the infrastructure side, the industry norm is that human error still accounts for the overwhelming majority of incidents. However, because of our designs and our highly qualified people, only a very small fraction of our incidents were related to human error, and none of them caused downtime. For as long as I've been building and operating data centers, I've been an advocate for efficiency and sustainability. It takes a tremendous amount of power to run at our scale, and we have to be good stewards for the environment to minimize our impact and reduce our consumption. We've been committed to sustainability since the earliest days of our data center program. We've been carbon neutral since 2007. We've received an A grade from the Carbon Disclosure Project for the last 2 years running. All of our sites are ISO 14001 and 50001 certified for environmental protection and energy management. And we're consistently at the top of Greenpeace's Cool IT leaderboard. Shamefully though, sustainability doesn't matter to a lot of folks in our industry. It isn't even a criteria in Gartner's Magic Quadrant for data center cloud providers. Well, it does matter. It matters to me. It matters to many of you, and it should matter to them. So thank you. Let's work together. Let's send a message to Gartner, have them get on board. Let's make this important, and let's make it a criteria. And for us, energy efficiency is truly at the heart of our data center sustainability program. We believe that the best energy saved is the energy not consumed in the first place. That's why we've pioneered hyper-efficient computing systems in data centers. And for that fact, our data centers consume, on average, only half of the energy compared to a typical enterprise data center. This has enabled us to be the first cloud provider to offer pricing based on Moore's law scale. But we are equally committed to powering our infrastructure with renewable energy. As a matter of fact, we are the world's largest private investor in renewable energy. To date, we've invested more than $2 billion in power purchase agreements. These PPAs are very important because, one, we are buying the entire output of wind and solar farms for long periods of time, typically 10 to 20 years. And these wind farms are on the same power grids as our data centers. And this gives the project developer the financial commitment and certainty they need to get the project developed. And so we know that our investment is adding renewable power to the grid that otherwise would not have been made available. And lastly, at the heart of our culture is innovation. No matter how good our systems are performing, no matter how well our teams are performing, we always believe we can do better. We have a relentless focus on innovation. In fact, since I've been at Google, we have redesigned our fundamental cooling technology on average every 12 to 18 months. And along the way, we've pioneered innovations in water-based cooling systems, such as seawater cooling for data centers, industrial canal water, recycled or reuse water cooling systems, rainwater harvesting, stormwater capture and reuse, and thermal energy storage systems. And we've designed data centers that don't use water cooling at all. Instead, they use 100% outside air cooled. So the point here is that there is no one-size-fits-all model at Google. Each data center is designed for the highest performance, the highest efficiency for that specific location. We don't rest on our laurels. We've also invested a lot in robotic innovation for our data centers. This is one example of a fully automated disk erase environment, which allows for faster, more efficient throughput and better inventory management of our hard drives. And lately, we've pioneered the use of machine learning and deep learning algorithms for data center operations. As you can imagine, our data centers are very large and complex. They're electrical and mechanical and control systems all working together to try and get the best performance. But the sheer number of interactions and operating parameters makes it really impossible for us mere mortals to understand how to optimize a data center in real time. However, it really is pretty trivial for computers to crunch through all those scenarios and find the optimal settings. So over the past couple of years, we've developed these algorithms and we've trained them with billions of data points from all of our data centers all over the world. Now we use this machine learning to help our teams visualize the data so the operations teams can know how to set up the electrical and mechanical plants for the optimal settings on that given day. And often these consider up to 19 independent variables that affect performance. This helps our team identify any discontinuities or any inflection points in the curves that might not be intuitive otherwise. Now, as you can imagine, with the explosive growth in public cloud computing, we've had some fairly aggressive expansion going on ourselves. So let's take a look at a short video, never before seen in public, of our data center campus in Iowa. Can you roll the video, please? Okay, what you're looking at right there, thank you very much. Yeah, come on. I mean, who doesn't love data centers, right? What you're looking at right here is the world's largest data center campus. Look at the size of the trucks. Those are construction trucks. Look at them for scale. Each of these building pads is over 1/3 of a mile long with multi-story data centers. We know that long-term capacity planning is very difficult. Everyone struggles with it, and we have been growing and keep growing to meet your needs and keep ahead of your needs. So with capacity like this, when you're ready to grow, we'll be ready for you. Thank you, yeah. Okay, so today, we have 13 operational data center campuses on 4 continents, and there are 2 more currently under development. Our global network brings our data centers closer together and closer to you. With more than 70 points of presence in 33 countries, this ensures the same low latency and responsiveness that you expect from Google's own services is now available to you on GCP also. And Cloud Platform is available at these locations, including our newly announced Japan and Oregon regions, and there's 10 more that are coming throughout 2017. And lastly, I'd like to remind you about our new 360 tour of our data center in Oregon. It's really cool. It's like a virtual walkthrough of one of Google's data centers. It's available in the playground area outside. And for those on live stream, you can experience it for yourself at the following link. So thank you all very much. It's been a pleasure being with you here today. Thank you. Thanks, Greg.
You know, one of the fun things about working at Google is working with people who are passionate about what they do. And I think that just comes across so clearly that Joe is passionate about his work. So that's data centers. Our second speaker and our second topic is about security. Niels Provos is a distinguished engineer at Google focused on security and privacy. Now, for context, there are only about 50 distinguished engineers inside all of Google. Now, and according to his Wikipedia page, in his spare time, he turns steel into swords. And security is different than many other features. It's an opportunity for us to work with you to create the best possible security environment for you, your customers. And with GCP, we have a great opportunity to put more and more of the tools that we use to manage our security into your hands so that you can manage your security as well. So with that, I'm really delighted and honored to bring up on stage Neil Provost, Distinguished Engineer from Google. Neil.
Thank you for the introduction, Greg. Good morning, everybody. As Greg said, I'm a distinguished engineer at Google. I am responsible for the security and privacy engineering teams. Today, I would like to pull back the covers a little bit and share with you a glimpse on how we pervasively secure you, your data, your customers' data, and your applications when you run on top of Google's cloud platform. However, let me set the stage a little bit first. At the recent Enigma conference in San Francisco, Rob Joyce, the head of NSA's Tailored Access Operations, made the following statements on how advanced adversaries manage to break into your systems and networks. Now, I understand that most of you would like to spend your time and focus on building a great product and great new features for your customers. However, your adversaries, they focus their time and energy on finding weak spots in your systems that they can exploit. Fortunately, at Google, I lead a team of experts who build systems and processes specifically designed to thwart adversaries. We do this by anticipating them, preventing them, detecting them, disrupting them, and containing them. And we will work with you to make sure that we can meet your requirements and that you can leverage our security capabilities on top of the platform. So now I would like to give you a little bit more insight in how we think about security at Google and how we have created a secure infrastructure for ourselves. Google's security and privacy team consists of over 500 people who continuously work to protect our infrastructure and you when you're running on top of GCP. Due to our scale, we end up seeing all kinds of bad behavior across the internet: phishing emails, malware websites, network attacks. And we also see all kinds of adversaries, ranging from all levels of sophistication, not just script kiddies and cyber criminals, but also nation-state actors. Now, at Google, we are not pursuing a hard-shell perimeter model. Instead, we are really focused on pervasive defense in depth. This is similar to the immune system analogy that Urs mentioned yesterday. There are two key principles running pervasively to our approach to security, and that is trust and transparency. That means that we design for trust throughout our stack, and we build in the transparency so that you can verify for yourself. And in fact, this talk is one of our steps in giving you more transparency. Now, I'll be talking about Google's infrastructure in the first part of the talk, how we think about security there. And then the second part of the talk, I will explain how that applies to you when you run on top of GCP. In order to facilitate this discussion, we have split our stack into 8 different layers. And I'll be walking from the bottom up, starting with the hardware, to the boot process, all the way up to deployment, operations, and usage. At the hardware layer, we are fortunate enough that we operate at such a scale that we can build our own proprietary secure systems. That means that we have purpose-built hardware for computing, storage, networking, all the way through to full data centers, as you just heard Joe talk about. Our ability to design and deploy custom hardware means that we can maintain provenance and establish trust at the hardware level. Now, on top of this trusted hardware, it's important that we can also boot in a trusted way. And to accomplish that, we have employed code signing that allows us to verify the BIOS, the bootloader, and the kernel. And that means that only the intended software can run on Google's infrastructure. So now that we know that our machines have booted in a known good state, it's also important that all of our jobs communicate in an authenticated and authorized fashion. To accomplish that, we have built a cryptographic key distribution system called LOAS that allows us to establish cryptographic identities for all jobs that run on our infrastructure. We know and audit the binaries that run so we can establish trust not only at the operating system, but also for the apps that are running on it. Now, we have heard a lot about virtual machines. And one of the properties we really need there is secure isolation. At Google, we use KVM as our hypervisor technology, and we have significantly invested to harden its security. That means that our security teams have found 15 of the last 21 publicly known vulnerabilities in KVM. That means that we are the first to fix and the first to patch, but of course we also contribute our findings back to the community so that everybody can benefit from a more secure KVM technology. And we continue on working to make KVM even more secure. To get a secure operating system image on our machines, we have created a Google-curated image that we run throughout our production infrastructure. This is very similar to the recommendation from the NSA of having a secure baseline. We have also deployed a service that alerts us of vulnerabilities in third-party source code to further protect our services. Now, at the storage layer, it's really important that all access to data is individually authorized and ACLed. Before we write data to disk, we chunk it and spread it so that not all data ends up on the same server. We also encrypt data and metadata individually. And to protect these encryption keys, we have built a system called KeyStore that wraps them by encrypting them further. Our storage systems only store this wrapped key and never the original cryptographic key that would be required to decrypt the data. And that means that all access to data requires an interaction with KeyStore, which gives us logging and auditing capabilities. Similar, for data in motion, we encrypt it when it travels between systems that we control. We accomplish fine-grained control over access with our internal IAM systems, and they also give us logging and auditing capabilities. So now at this point, we are running on trusted hardware. We know that the boot process was trusted, and we trust our operating system. And we also have provenance for hardware, boot, and OS. We encrypt the data, and we know that all access is authenticated and authorized. Now, to secure our applications, we're pursuing multiple layered approaches. One of them is that we have built a binary on configuration verification system. That means that for all applications, we know how they were built, we know how they were configured, and we know how they were deployed. And for each of these steps, we know who was responsible for them. To put additional security into our development process, we require that all code gets peer-reviewed. That means there's a second pair of eyes that looks at the code before it's being committed so that we can find bugs and security problems very early on. To help our teams create more secure systems, we also require a security review before anything can launch. That means that we can put security into our products right at the design phase. However, even with the best practices, you still cannot prevent all security problems. And so we have created a security scanning technology that allows us to find many of the common mistakes: cross-site scripting, mixed content, mixed pinning, more strange attacks such as Rosetta Flash. And we have also used this as an example and where we can contribute back to the community. We have made our firing range testbed open source. That is, if anybody else would like to develop their own security scanning technology, we already have a ready-made app that they can test against. So at this point, our applications are reviewed, they have been tested, we believe they don't have vulnerabilities, data is encrypted, and access is authorized. But now it's time to expose these applications to the dangerous web. And there are multiple different ways in which we secure our applications there. First of all, on the network, we protect the traffic with TLS. To prevent man-in-the-middle attacks, we have put certificate pinning into our Chrome browser so that we only trust the right certificates. We have also deployed unphishable user identity to our users with unphishable hardware second factors. And to protect against network attacks, we have built-in DDoS protection. Some of you might have heard recently about Project Shield, where we announced that we are extending this DDoS protection to news and human rights organizations, as well as election monitoring sites. Thank you. At the operations level, we have built technology that allows us to patch and monitor, do incident response, forensics, threat analysis, and threat intelligence. And this is also another example where we have contributed back to the open source by making some of our forensic tools available, such as GRR or Recall for memory analytics. Now, one of the sayings that we have is the first user who is going to be hitting your application is likely going to be an app user. So we give our developers tools to be able to do reputation checks on URLs and binaries. We have automated analysis of traffic to find botnets that might be engaging in spam. And we also leverage our global view on badness to build threat intelligence on bad actors and current attack vectors. However, to reduce the overall attack surface that we face and that our users face on the internet and that all of you face, we created Project Zero in 2014. That is a team dedicated to finding zero-day vulnerabilities in critical internet software. You may have heard about the Heartbleed bug in OpenSSL, Urs mentioned that briefly yesterday, or about Rowhammer, where just reading memory can lead to remote code execution. Most recently, we announced a widespread security vulnerability in glibc. So that means that we have a team that finds critical security problems that are very widely spread. And we get the benefit of knowing about these first so we can fix our own infrastructure, but we can also work with the rest of the community to make sure that we get the internet infrastructure fixed in general. As I mentioned in the previous slide, writing secure software is difficult. And Google has been one of the first companies to create a vulnerability rewards program where we ask researchers across the world with helping find security bugs on our products. And just last year, we paid out over $2 million to hundreds of researchers who helped us build more secure products. So now let's switch over to GCP. I've just told you, and I hope you understand a little bit better about the security capabilities that we have built for ourselves. You might wonder, that's great, but how does that apply to us and when we run on GCP? These security capabilities that I mentioned to you is what enables our Google developers to live the V3 cloud experience, the next cloud experience. It means that they can focus on building amazing products and they do not have to be security experts. Now, we understand that many of you are on a spectrum on how you develop and manage your applications, and that all of you are going to be in different points in your journey to this next version of cloud. We understand that you may have to manage and segment your network to create trust zones, or that you need more explicit control over the firewall and the network perimeter. All of you need logging and auditing capabilities. And we are really committed to help you meet your goals wherever you are on your journey to this next version of the cloud. And to accomplish that, we are increasingly making more of these capabilities available to you, and I'll be explaining to you a little bit how that is going to look like. So I mentioned previously we had 8 layers in recognition of the need that many of you need better control over the network. We have introduced a network layer here. So I mentioned to you what it is that we do at the hardware level, what it is that we do for our boot process, and at the operating system level. You're actually benefiting of all of these mechanisms already because GCP is built on top of these. Many of you have also compliance requirements, and our infrastructure is regularly audited by external auditors for SOC 2 and 3, ISO 27001, PCI DSS 3.0, and for Google Compute Engine, Google Cloud Storage, Cloud SQL, and BigQuery. We are also covered under the HIPAA BAA. That means that you can build on top of an infrastructure foundation that is regularly audited and certified. For cloud, at the storage level, all data is already encrypted by default. To give you even greater control on how data is being stored at rest, we have made customer-supplied encryption keys available to you, and we also give you audit logging capabilities. In the future, we plan on giving you even more control with a key management system that allows you to manage your own keys, generate them, rotate them, suspend, resume them, delete them, or manage the import and export of secrets. Yesterday, you have heard about our IAM system that we have now made available to you, which gives you explicit role-based access control. And we will give you additional capabilities later on in the year. Now, at the network layer, many of you require explicit control. In fact, today, there are already many ways in which you can customize your network, such as with isolated IP groups, private IP addresses, VPNs, or inbound firewalls. We are working on extending and expanding these features, including outbound firewalls. When you run on Google App Engine, you already can benefit from the security scanning technology that I had mentioned to you earlier with the cloud security scanner. We're working on creating more scanners and on increasing the scanning capabilities so you can also use it on GCE and GKE. We also plan to give you the ability to sign your binaries so that you can verify and enforce what gets to run as part of your infrastructure. We are also thinking of giving you source code security capabilities. However, that requires that you first store your source code with us, so please check out the Google Cloud source repositories. For protecting your developers and users, we already give you the options of using security keys, which give you this unphishable hardware second factor. Many of you at the moment may be relying on this sort of hard network parameter that I've been talking about earlier. We also plan on giving you detailed and sophisticated identity and authorization tools. That means that you can write access policy not just based on the user, but also on the machine and location. You may have heard about the Beyond Corp model yesterday. That sort of goes in that direction. When you leverage Google Scale by using, let's say, the HTTPS load balancer, you also benefit from built-in DDoS protection. To protect your SSL and TLS certificates, we have been working for years on something that is called certificate transparency, that essentially creates publicly verifiable logs that give you provenance and trust for the certificates for your own domains. For operations, you already benefit essentially from all the practices that we have for the underlying infrastructure where we regularly patch and upgrade. However, for your own projects, we are looking into giving you an integrated view that gives you an idea of the patch level and vulnerabilities for your own deployments. And we're also thinking of ways of adding some of our threat intelligence into that view. You already can benefit from audit logging and Stackdriver to give you a better idea and detailed records of what's going on with your infrastructure and your data. In the future, we plan on giving you StrongAuth. This is a hardware second factor for logging into your projects. But we're also investigating additional app use signals that we might be able to make available to you when you develop your applications, such as URL and binary reputation. So these are just some of the security capabilities that we will increasingly make available to you to access and control. You already have the option for us to manage the security on the platform if you use, for example, Google App Engine. But we also plan on giving you the ability to leverage an increasing array of security features that you can manage to your own requirements. And to be clear, our goal here is to provide you the control you need on a trusted and transparent cloud so that you do not have to become security experts, but can instead focus on innovation and creating a great business. Thank you very much.
Thanks, Niels, very much. Our final topic we want to talk about is the evolution in containers. And who better to talk about that than Eric Brewer? Eric is a pioneer in cloud computing. In fact, before coming to Google, he built one of the world's first scalable clusters. He's been involved in industry and academia as being on the staff at UC Berkeley. He's been a champion inside Google for this notion of a move to a third wave of computing driven by what we can do in containers. He's going to talk about Kubernetes, and he's going to give you a view of some of the deeper implications and where we see this technology evolving over the next few years. So would you please join me in welcoming on stage Eric Brewer. Eric?
All right, thank you so much, Greg. If you were to ask me what my job is at Google, I would, having now thought about it a little bit, say, what's next? That's a fun job to have. Today we'll talk about containers, which for the past few years have been what's next, and we've made a lot of progress on that, especially through Kubernetes. But I also want to talk about some things we haven't gotten to. So I view this era as kind of the cloud-native era, and what I mean by that is the applications you build are built to run natively in the cloud. You're expecting to make use of cloud resources. You're expecting to have an infinite number of machines, essentially, and things you can easily scale. Right, so that's a wonderful place to be. It's built on top of containers. That's certainly an important part of it. It's very dynamic because you can change not only the number of services you have, the kinds. For example, with custom images, you can have as much RAM or CPU as you want. There is no physical machine like that, actually. So these are literally virtual machines in that sense. And we're moving to a model of microservices, not so much because we want the services per se, but we want the decoupling that the services give you so that you can have a lot of people and a lot of different teams working well together. So this has been enabled by Kubernetes, and I'll talk about that some today. In particular, the way it allows you to do production versions of containers. But one thing we haven't really gotten to is so fine, I can have a container, I can schedule it, but how do I actually manage my whole app and evolve it? And how do I configure it? Because when I think about things that have been tricky inside Google, configuration actually is always at the top of the list. And I would say when we have software errors internally that cause problems, configuration errors are high among them. Right? It's kind of a nasty little area that's hard to get right. And I'm going to talk about what's next for that in particular today, hopefully make some progress. Now, we've been using containers for more than 10 years. Our definition of containers didn't start with Docker. It predates that by a long way. It started really with Linux containers, which we were putting in for performance isolation. So the first thing we want out of containers is performance isolation. We did this through C groups, which we contributed to Linux about 10 years ago. Namespaces have been added. There's lots of features that are about the isolation aspects of containers. And that's what gives us high utilization, so we can run many different jobs on the same physical nodes. Docker came along and did a really nice job with the packaging. We have had packaging inside Google for 10 years of various flavors, but I will admit the Docker version for packaging, at least, is a little cleaner. In particular, they have an overlay file system that allows you to compose different pieces into a single entity, and it does a nice job with how you handle libraries. So for example, your container is immutable. It includes the libraries you need, and therefore it runs the same on a laptop as it does in the cloud. Right? And then we'll come back to that point about immutability because it's something I want to build on. On the Kubernetes front, it's really about trying to bring the way we think about using containers production to the cloud. In particular, we started with Borg and Omega. These are, Borg's more than 10 years old at this point. That is the scheduler for the internal jobs at Google. But it's actually more than just a scheduler. It's actually implicit in its ecosystem is things like load balancing and naming and discovery and health checking and how you move jobs around. And so we wanted to take the lessons from Borg and rebuild them into Kubernetes, which I think we've done actually quite well, and then talk about how you use that to get a Google-like experience. And I'll say what that means. In particular, the biggest change between Borg and Kubernetes is not the functionality, it's the fact that Kubernetes is open source. Right? Borg is a complete giant monolithic thing that we couldn't possibly open source, and you wouldn't want it if we could, actually. Right? But it's a great thing to learn from, and Kubernetes takes the best of it and has really made it something that is much more usable and much cleaner. So despite being only 20 months old, Kubernetes is already in the top 0.01% of GitHub projects. It's had 27,000 commits, which is a crazy number. In fact, we had to add staff just to deal with pull requests. The pull requests you get when you have that many commits is crazy. Right? So that is a very healthy sign of the community, and that's really the reason we open sourced it, is to get that community participation and, frankly, to enable hybrid and multi-cloud deployments. So these two work together, Docker for packaging and Kubernetes for management of containers. And so what do I think of as the things that Kubernetes needs to provide, which are equivalently the things that were in the Borg ecosystem, In particular, it's things like how you provision the nodes and attach the storage. It's how you connect to the containers both directly, which is actually not the case that matters, and indirectly through load balancing. So deep in the kind of design of Kubernetes is how you do load balancing, right? You kind of can't use Kubernetes without automatically using load balancing all over the place. And that is pretty fundamental because load balancing is actually really about availability. It's how we decouple which pods are up from the name of the service that you're using, right? So as long as the load balancer is up, your service is up, and it can have 1 pod or 10 pods or 100, and we will vary those numbers. We actively monitor the health. We find that for production operations, you have to actually know which pods are up and running correctly. One of the changes we've made is to make it easier for you to tell us when a pod is working correctly. We'll ask you, is this pod working? And if the pod can say yes or no, right? That ends up being a very robust way to build systems. Scaling, of course, is critical to this. This is also inherent in the load balancer, right? So I'll do a lot of auto scaling. I'll talk a bit more about that in a minute. And finally, I think the most important part, if you said, what's the essential differentiator for Kubernetes, it's really about evolution, which is the orchestration. Right? Kubernetes makes it really easy to have a running service and upgrade that service while it's running to a new version. Right? That is historically hard to do, and it's a super important operation. Right? You can't take your service down to upgrade it. That's not okay. Right? And particularly when you get to more complex projects, you'll find you have many different teams building parts of a larger service, and you really want every one of those teams to have their own independent updates. That's what you get, how you get velocity. So that's what you want out of Kubernetes. There's a few other things I want to get across about just the core of it that I think can always use a little more explanation. One of them is this thing that, what is the cluster? And it's because it gets to how we think about Borg. So a pod is a collection of containers. That's the unit of deployment. The cluster in Kubernetes is essentially a collection of nodes that you deploy pods onto. And the Borg equivalent of this, essentially, I think of it as being the sea of resources. When you're programming internally at Google and you want to run your job, Borg gives you this literal sea of thousands of places that job can run. And you don't think at all about specific machines, right? Your interface to the system has nothing to do with machines. It has only to do with these places that can run containers, right? That is a wonderful place to be. So the point here is, if you have this notion of a cluster that's more like a virtual cluster, it is decoupled from the applications that run on it. So that means that one team can manage the environment that you run on, and another team can actually run the application, right? And that makes all the teams more effective. So that's an important decoupling, the environment that you run on from the actual application you're trying to build. And of course, in Google, like in the cloud, we actually have one big collection that lots of different things can run on, right? So that's actually part of the fun of the schedule. The same decoupling should apply for services. So when I say services are independent, or what's the goal of a microservice, my primary goal is that it is independently upgradable, that you could upgrade this microservice even with other parts of your application not changing. Because that's what gives different teams high velocity, so that I can have a team that's going quite quickly here, unaffected by whatever's going on in other teams. That's hard to do, and microservices done well give you that structure. Oh no, shoot. Maybe we can go back one slide. Thank you. I'm happy to announce that GCP Next 1.2. This has been a tremendous amount of work by lots of contributors over the past few months. It has a lot of interesting features. I think the most obvious one is scale. You can now run jobs that can run on 1,000 nodes with up to 30,000 pods, and that is huge. A highly requested feature, and really means that scaling is not a practical limit for almost every team. I'd be surprised if you need more than 30,000 pods, but if you do, great, we're happy to host you. You can be our new favorites. Some of the things in 1.2, much better control over ingress, especially layer 7 load balancing, jobs, which are a way to do batch scheduling. So now you can do batch scheduling, batch jobs in Kubernetes. Daemon sets are allowing you to have a daemon running one per node, which allows you to do certain kind of housekeeping things like log rotation. An API to manage running deployments, to give you aggregated statistics, for example. And config map, which I'll talk about in a little bit, which is a new way to do configuration. So back to configuration. So configuration is kind of a mess today, I would say. It's unsolved, as maybe. Not mess is too strong a word. So we're good at building things. We have processes for that are pretty clean. We're pretty good now with containers at packaging those things into runnable systems. Then when you deploy it, it's kind of a collection of scripts and command line arguments and things that are highly variable. And it'd be nice to see if we can improve that. So the two most common approaches, and we use both of these internally, are scripting and configuration languages. Scripting is just what, like you say, you write scripts to actually configure your nodes and put them in the right state and start the software. This always works. It's eminently powerful. It can do anything, but it's very fragile, right? We find that, if something stops in the middle of an initialization script, now you're in this weird state. You don't know how to fix it. So how do you get back to a good state? It's very fragile. So I don't like to use scripts running at deployment time. Another approach, which is a domain-specific language for configuration. Actually, we've built many of these inside Google. We don't have just one, we have several. And they are good in that they're less verbose, they're specific for configuration, so they're very efficient. But they have problems too. For example, if I add a new thing I want to configure, I have to also add it to the language before I can use the language to fix it. That's the lagging problem. The other problem is when you have a new language, you don't typically have all the debugging support and tooling support and Emacs macros and all the other things you might want to actually make it usable. So I think we should try a new approach that goes back to the idea of immutable infrastructure, because that's really what we're getting out of containers. We're getting immutable packaging. Even pods are a kind of immutability. Pods give you a group of containers that's immutable, and they also give you immutable port numbers, which means if you change IP addresses, all the port numbers stay the same. It actually is quite handy. Internally at Google, we don't get that, by the way, because we run multiple jobs on the same machine. They share IP addresses, which means you can't count on any particular port address being available. So, and yesterday we saw Spinnaker doing lots of work with this immutable infrastructure focus for how you configure things. But really, taking it a step farther, I think the core new idea that's in this talk is the structure of a multi-node deployment ought to be immutable too. The structure, right? So in this model, you construct a graph that is immutable, that represents what you want to run, and then you deploy that graph onto actual resources. So I've broken deployment into two steps, a construction step, which is immutable, and a deployment step, which is something you do actually once you know that you have what you want. So when you think about it this way, it's really that we'd like to have this new model of construction. We want a couple properties. We would like it to be a simple declarative framework. I don't want to use a lot of scripting. I don't want to have a domain-specific language. So the idea here is I'm going to have a minimum DSL, which is really YAML plus some parameters. And if you need code, we're going to use it to construct the graph, not at deployment time to run on the nodes. Because construction is an offline operation. If it doesn't go well, we can redo it. Right? We haven't actually deployed anything when we're doing construction, so it is a low-risk operation. The second thing we need out of construction is it has to support encapsulation and composition so that we can build complicated things that have some modularity. Even if we did that, we would still need some actual runtime configuration because the graph is not sufficient for a deployment. In particular, two things don't fit. One of them is keys. I don't want to put my keys in my container. Oh, by the way, I see people do this. Don't do that. Bad idea, right? People can see your images, and they can see the keys inside the image, right? So the Kubernetes answer to that is called the secret volume. And it's basically a mounted volume in which your secrets are stored, and we connect that volume to the right node at deployment time. So it's totally out of band from the packaging path. That's the right model. Now, with config map in 1.2, we're extending that idea to generalized config. So any configuration you want for a pod, instead of passing it in through flags or environment variables or some other path, we're going to put it in a volume, and you mount that volume. And it has a lot of advantages. In particular, the volume itself can now be part of construction. I can build a graph and say, these are the volumes that contain the config and the secrets that we want to use at our deployments. We can now update config in a reasonable way. Like if you want to update config using environment variables or using flags, you have to restart the service, right? In this model, it's a volume, it's attached, you can just rescan the volume, right? So it makes updates simpler. And finally, puts all the config in one place that's easy to have auditing and source code control over, right? So the configuration is, you can look in the volume and see what's there. It's very clear what the configuration of a running system is. One problem we have inside Google is that after a job is running, we don't know how it was configured, right? We can't introspect to see exactly how it got set up. That's a mistake, right? We're not repeating that mistake with Kubernetes. So now if I go back to the flow of configuration, I would say we do our build, we do our packaging, and now we do construction, which is we define the topology of what we want to deploy. In this case, it has a front end and a back end with multiple nodes. By the way, I don't have to fix the number of pods in horizontal scaling. When I say fix the structure, I'm saying this is a variable size front end, but I don't have to know what the size is. That I can change at runtime. Then once I know what I want to deploy, then I can deploy it, right? And that's a separate step. So really, we have a mounted volumes for our secrets, we have a construction phase, and a deployment phase. This leads to the final little bit I want to talk about, which is I just told you conceptually about the idea of construction, but I haven't given you any tools to do it. And so the last part is the tools to do that. And so our approach on this is to make these graphs be essentially a type system. So we're going to have a type for everything you want to build. So if you want a front end, that's a type, right? And the mental model I have for this is constructors, as in Java or C++. So I have a constructor with arguments. It builds an object of that type, right? And it's a thing that runs once at construction time, and it gives you an immutable output, which is the parameterized resource. So these nested types have meanings that are useful, right? That really is front end is a thing with meaning, and you can have one team define the front end and another team use it because it's a well-defined type. These graphs can get quite complicated, and so we do use code, but not for scripting. We'll use it at construction time. So for anything you want to construct, you can have construction time code, currently Python and Jinja, that can actually generate the graphs locally using whatever logic they want. So that's actually hosted. You can use that to decide how you want to build your system. The instantiation of this so far is Google Deployment Manager. This is a new framework that gives you essentially a way to use parameterized templates with this kind of recursive resource construction, which I'll show you in a second. In particular, it supports the construction model and the deployment model separately. It does both, but they're actually separate things. And then what you get out of this overall is you get the ability to have not only deployment manager for all of the Google primitives, but you can make your own. So essentially, this is an extensible type system. You make your own types, you share them with your teams, and then they can build on them, right? So here's an example. It's going back to the constructor idea. It's really parameterized template. So the YAML file is the arguments to the constructor, and it says, oh, this is a thing with a front end and a back end that runs in US Central 1, and this is the production version, not the testing version. That is the input to a type, a template, which when you execute, produces separately a front end and a back end. And these are in black because I want you to think of these as black boxes. Some other team may have defined what a front end is and what a back end is, and you're using them in your type. So we do get encapsulation. Now, expanding those out, they are just types themselves that have parameters and templates. And they recursively get expanded, and they'll actually expand to, oh, this is how you implement a front end. It has these kinds of nodes with these disks. It has this load balancing settings, these firewall rules. That is inside the definition of the front end and the back end, respectively. So we're getting actually that recursive graph structure through this construction process. Now we have a immutable, well-defined description of our deployment, and now we just deploy it, right? And which means that'll be a repeatable process and very easy to make sure that it gets done exactly right. Very robust. I'll just go through this relatively quickly. This does fit well with this model of secrets and config. Because again, the structure includes the secrets volume and the config volume. And so when we do the deployment, you kind of wake up and on your pod is the data you need for configuration and for the keys, right? They're just magically in the right place. Finally, it's not enough that this be something that we can use on GCP. We are the open cloud, we believe in open source, and this is an open source project itself. So we've been working with Deus on their Helm project, which we're fans of, and we've added this construction capability working with them to Helm. And you can go check this out on GitHub. I would say it's almost ready. It's definitely in progress and usable and interesting. They have a notion of a chart, which is very similar to our type system. So we extended that to include this kind of construction. There's an example, the Helm install Redis cluster. That basically means Redis cluster is a defined type of a thing that they made, and you can now install it as a thing, right? That is the deploy step given the construction. All right, that's what's next for config. I'm super happy to be here today, and thank you so much.
Thanks, Eric. I love, while Eric was talking, I saw an analyst from RedMonk tweeted, "Fanboy moment, Eric Brewer on stage." That's my day every day I come to work, is I get to work with people that are just amazing thinkers, doers, and builders. That wraps up our day 2 event this morning. I want to thank you again for your time, for your attention, for your contributions to everything that we do in Google Cloud Platform together. I hope you enjoy the rest of your day here at the event, and please interact with us online and here and throughout the coming weeks and months. Thank you, and enjoy the rest of your day.
Your GCP Next host here. Hope you enjoyed the keynote.
Next up, there's some exclusive online content for you. First, there's a session on infrastructure in the cloud, immediately followed by a session on the Google Cloud Data Platform.
And just like yesterday, if you have questions during the session, just scroll to the bottom of your screen. You can put a question in the Q&A box there and get a live answer.
Enjoy.
Hello and welcome. I'm Navneet Juneja, and I am the product lead for compute platforms at Google. It almost feels like if you blink, you might miss the transformation of computing infrastructure that's sweeping the industry today. Not so long ago, infrastructure was boring, something you spent a lot of time on because you had to. Today, it's dynamic, agile, and a source of competitive advantage. And yet, it can fade into the background so you can focus on building and running the applications that your business depends on. That's the power of cloud infrastructure. At Google, we think about infrastructure not as a monolith, but rather as a series of layers of abstraction. Physical infrastructure, cycles, bytes, and networks, is the foundation on which everything else is built. Virtual infrastructure abstracts away the physical infrastructure and makes it programmable, dynamic, agile, and accessible, but still has the familiar feel of cycles and bytes. Finally, there's logical infrastructure, which shifts the focus from cycles and bytes to application building blocks. And of course, above infrastructure, Google Cloud Platform also offers a variety of more vertical, specialized platforms and services that do specific things really well. But my focus today is the infrastructure. When you think about Google, the first thing that comes to mind is probably this deceptively simple page that gives you answers to even the most obscure questions in milliseconds. But the heart of Google is a massive computer. Not a computer in the traditional sense, but the first true cloud, a collection of state-of-the-art data centers connected by the world's largest software-defined network. We didn't set out to build a cloud, although in retrospect it was inevitable. We had to build it in order to build Google. And in many ways, this massive computer is the heart of all innovation at Google. Not just because it exists, but because we've built it to fade into the background so that our engineers can focus on what they do best, building reliable applications at internet scale. Because it's the core on which everything else is built, it has to be great. And now, Google Cloud Platform makes this computer available to you. We innovate at every layer of the stack, from hardware design to how we build, operate, and cool our data centers. As a result, our data centers use half the power of a typical data center. That's good for the planet and for your bottom line. In addition to using less energy, we also care about where that energy comes from. Today, 35% of our energy comes from renewable sources, and the rest is covered by carbon offsets. But we're not stopping there. We have a goal to power our data centers with 100% renewable energy and have made agreements to fund over $2 billion in renewable energy projects whose impact extends beyond Google. The network is the cornerstone of the cloud. You can't do much with hundreds of thousands of servers if you can't access them quickly and reliably. Google's network spans the globe with edged locations in over 30 countries connected by our own fiber, even across the Atlantic and Pacific, which allows us to get bytes to the end user faster. Once again, we built this because we had to. It's how we deliver a great experience to our users. Now you and your customers can benefit from our network, the broadest reaching network of any cloud provider. Of course, almost nobody wants to work directly with physical infrastructure. Virtual infrastructure gives you familiar building blocks, but frees you from the cost and complexity of planning, deploying, managing, and operating physical infrastructure, giving you completely programmable building blocks that you can change whenever you need to. Want to give your database more RAM or your render job more CPU? It's a click or API call away. Want to change your networking? That's just as easy. This enables an unprecedented level of operational agility and flexibility. You're no longer bound by hardware acquisition cycles, fixed costs, capital expenditure, and teams of operators reconfiguring physical machines. Virtual infrastructure gives you familiar building blocks, but with infinitely more power and flexibility. And here's how it works. Let's create our first VM. Everything in Google Cloud Platform lives in a project. I'm going to use an existing project here. If you don't yet have a project, you can create one online at cloud.google.com. We're going to be using the Cloud Console UI, but you can do everything using the command line too. Next, let's go to the compute section of the console. Here we'll click Create Instance, name the VM and choose a location for it. This screen has pre-selected defaults for almost everything, including the size of the machine, boot disk type and size, and the disk image that will be used to create it. By clicking the Change button, we can use a different predefined image or one of our own. We can also use a disk snapshot to create the boot disk, or use an existing disk. Let's use the defaults for now. We can also set up the VM so that it can directly access other cloud services. And we can open up access to HTTP and HTTPS on this machine right here. Since we're going to run a web server, I'm going to enable HTTP access. By clicking on the Advanced drop-down here, we can do things like specify various management options, including a script the VM should run when it boots. Change networking settings, change disk options, and more. I'm going to use a startup script that installs and runs Nginx, a popular web server. Let's go with the defaults for everything else, and click Create. And in a few seconds, we'll have a VM. The notification above tells me the VM is created. I can see the output of my server by pointing my browser at it. And I can SSH to it from right here in the browser. I could even turn this into an auto-scaled load-balanced service. And if I want higher availability, I can set it up so that the front ends are distributed across zones. If you'd like to see scaling and load balancing in action, please watch the auto-scaling video on the Google Developers channel on YouTube. In addition to spinning up a VM from scratch, you can also use the Google Cloud Launcher to launch pre-configured VMs with common software stacks. Google's virtual infrastructure also offers many benefits that you can't get elsewhere. For example, we're the only hyperscale cloud provider that performs transparent maintenance on our physical hosts and SSDs. Why do we do this, and how does it work? All infrastructure needs maintenance. The host OS needs regular patching to keep it secure. Power infrastructure needs maintenance. RAM chips fail and need replacement. The list goes on. But many forms of host maintenance are disruptive to the host, and the way other providers handle them would require, at the very least, rebooting all the VMs on the host. There are two common ways used to manage maintenance. Delay maintenance as long as possible, which raises the risk of security issues or unexpected failures, or regular planned and emergency maintenance that affects all running VMs. We chose a different path. By combining innovations in data center architecture and operations with live migration technology, we move running VMs out of the way of a host maintenance event without impacting the running VM. So your VMs keep running while we keep the underlying infrastructure secure and reliable. We also use this technology to improve reliability by moving VMs off impaired hosts when we first detect hardware failing. Google is not just a great place to build reliable, scalable apps. It's also great for workloads that are non-time critical or short-lived and bursty. Need tens of thousands of cores for a week? No problem. Preemptible VMs allow you to run workloads that can handle occasional preemption at less than a third of the cost. Since the launch of preemptible VMs, they've been used for a variety of needs. For example, Descartes Labs is using preemptible VMs for massively parallel image processing. Movie production firms around the world are using them for short-term, massive burst rendering needs. They're helping bioinformatics and genome processing users migrate to the cloud and lower the costs of genome sequencing, enabling breakthroughs in personal medicine and pharmaceutical research. Travis CI is using Compute Engine and preemptible VMs to run the next generation of their continuous integration build service. Custom machine types let you tailor your infrastructure to your workload, rather than the other way around, so that you can build a machine type with the exact amount of CPU and RAM that your application needs. This could save you a bundle too. Customers using custom machine types have saved an average of 19%, and in some cases, as much as 50%, using custom machine types. And you get access to this virtual infrastructure at a great price. Not only because our rates are low, but also because of how we structure our prices, so that you only pay for the resources you use when you use them. In addition, unlike other cloud providers, you don't have to reserve resources with upfront payments and commitments to get our best prices. We apply automatic discounts to your sustained workloads so that you get all the cost advantages without needing to plan and commit to resources well in advance of their use. And independent analysis by the Enterprise Strategy Group shows that depending on your workload, you can save as much as 88% by using Google Cloud Platform. So that's virtual infrastructure. It's simple, yet more flexible, powerful, and cost-effective. Logical infrastructure raises the level of abstraction further and frees you from thinking about machines, virtual or physical. The focus is now on the components of your applications, how they interact, how they are orchestrated, operated, and updated. Logical infrastructure lets you focus only on the portions of the stack that matter. The machine and even the operating system fade into the background. Google's way of solving this problem was adopting a cluster-first approach to application development, where the focus is on the application components and the resources they need. This shift is tremendously powerful. The path to modern containers started at Google. In 2004, Google engineers contributed much of the code in the Linux kernel that supported C groups and namespaces, the underlying technology that enables containers today. everything at Google runs in a container. We spin up more than 2 billion containers a week. The three key benefits that we've realized with containers are portability, repeatability, and abstraction. Portability and repeatability come from the fact that each container image includes everything that is needed to run the process it represents. But the big win is abstraction. By abstracting the app from the OS and the machine, we can create a clean separation of concerns between application development and maintenance, and infrastructure deployment and operation, which in turn means greater agility for Google because the teams can focus on what they do best. Now, running a container is pretty easy. The hard part comes when you have to manage containers in production. How do you route traffic to them? Wire loosely coupled components together? Collect logs? Manage health for the container and application? Recover from failure? Roll out a new version? Now imagine doing that with all your applications sharing the same underlying infrastructure. The transition from development to production with containers is where the rubber meets the road. At Google, we understand running containers at scale, so we built Kubernetes to solve that problem for you. Kubernetes and its hosted version, Container Engine, are the successors to Borg and Omega, the platforms that all of Google runs on. In mid-2014, we released the first version of Kubernetes based on over 10 years of running containers at scale. The flip side of the simplicity that containers enable at the application level is that you only get the full benefits of the model when you have a sophisticated orchestration layer. Let's look at a common example. Have you tried to run 5 web serving containers on the same machine? What happens? You get port conflicts that you have to solve yourself. So you give them all their own ports. Great, but now let's say the one running on port 83 failed, and now you have to start a new one. Do you restart it on port 83? Or give it port 85? How do you know which port is available on which machine? And how do you load balance across these containers? So when we were designing Kubernetes, we took care of that problem for you using software-defined network IP addresses that Kubernetes manages for you. You define what you want to run and the endpoint that it exposes internally or externally, and Kubernetes wires everything together and keeps it wired together as containers come and go, application components change, and your application evolves. That's just one example of the kind of things you don't have to worry about when you use Kubernetes. There are so many more. Health checking, service discovery, log aggregation, load balancing. It's all in the box and it's production ready. And that's why enterprises are betting their businesses on Kubernetes. The New York Times, SoundCloud, eBay, and Zulily, and thousands more are running Kubernetes and GKE in production. Let's talk about the key concepts in Kubernetes and Container Engine. A cluster is a collection of resources within which your applications run. Nodes, which are physical or virtual machines, network, and storage. Once you have a cluster, you can forget about the underlying resources and focus on what you want to schedule, a task that the master does for you. A pod is the unit of deployment. A pod is a collection of one or more co-located containers and volumes. Containers in a pod share process, network, and IPC namespaces. A replication controller ensures that a specified number of identical pods are running at any one time. It can be used for scaling, both manual and automatic, health management, rolling updates, and more. A service is an abstraction which defines a set of pods and the means by which to access them, like a stable IP address and corresponding DNS name. The cluster provides various mechanisms for discovering these services once they are defined. An example of a service could be your web front-end tier. A job allows you to schedule a transient workload into a cluster, create one or more pods, and terminate once one or more of them have run to completion. So for example, you could use a job to run a large-scale computation. Let's see logical infrastructure in action. This time, I'm going to use the command line. First, let me create my cluster to run my workload. This will take a while, so I'm going to skip ahead. Now, what's the first thing you might want to do on a cluster? Run a container. Let's run a container running Nginx. Nginx maintains a public Docker image, so I can just use that. So what has happened behind the scenes is we've created a replication controller that runs one instance of a pod with an Nginx container in it. So if something happens to the pod, the replication controller will automatically bring up a new one. Let's see the running pods. Let's scale this up. Let's look at the pods now. Okay, all looks good. Okay, now let's expose this to the world as a load-balanced service. It will take a short while to create and wire everything together. Let's take a look in the browser. That was pretty easy. Now, if you're doing this in production, you probably have a more complex set of components, and so you'll want to use a declarative approach. Tell the system what state you want, and have the system make it so. This makes everything repeatable and easy to understand. That's built into Container Engine and Kubernetes. Let's take a look at a config file that deploys a replication controller with a more advanced pod specification. The pod specification is in the template section of this configuration file. The pod has 2 containers and a storage volume. One container is running BusyBox and writing an index file out. The Nginx container is mounting the volume to which the index file was written and serving it. This is possible because containers in the same pod can share volumes. Let's delete the old replication controller and use this more advanced version instead. And let's look at it live. You can use replication controllers and services to do rolling updates, canary or A/B experiments where you only send a small percentage of your traffic to a new version of the application, and more. So as you can see, Kubernetes and Container Engine allow you to think about compute and storage as a pool of resources that you schedule applications to run in. Just provide the desired state for your application, and they will ensure that your application is constantly in a healthy state. That's the power of logical infrastructure. And that's our cloud infrastructure. From the physical layer that underlies everything, to virtual infrastructure that gives you a familiar building block that is infinitely more powerful, to logical infrastructure that frees you to focus on the application. Choose the level of abstraction that's right for you on Google Cloud Platform. Thank you for watching.
Good morning or afternoon. I'm Fausto Ibarra, Director of Product Management for Google Cloud Platform. I'm very happy to talk to you today about all the great things we're doing at Google around data and analytics. As you all know, data is everywhere. It is becoming a critical part of our lives and our work. Whether we're talking about sports statistics, global warming, or the latest elections, we use data all the time to communicate and to make better decisions. At Google, data is at the core of what we do. Our mission is to organize the world's information and making it accessible for everyone. We're constantly working on new technologies to process very large amounts of data in the petabytes and exabytes. We have built an incredible infrastructure to support our many products and services, like Android, YouTube, Google Maps, Gmail, and of course, Google Search. They all run on Google's data centers around the world. Over the years, we've developed many groundbreaking technologies to process and analyze vast amounts of data. We've shared many of these technologies with the industry and our customers, first as research white papers and then as public cloud services. Our papers on Google File System, MapReduce, and Bigtable started Hadoop and the big data revolution. Dremel, our infinite data warehouse, used extensively at Google, is now available as BigQuery to be used by any customer around the world. Most recently, we have shared our innovations in batch and stream data processing with Dataflow, which has become Apache Beam. And we have introduced TensorFlow, one of the most active open source frameworks for machine learning. Now, Google Cloud Platform has an incredible collection of cloud services for data and analytics. We have reliable cloud storage, databases for all kinds of applications, such as Cloud SQL and Cloud Bigtable, big data services for batch and stream processing, such as BigQuery and Cloud Dataflow, and groundbreaking machine language services, such as the new Cloud Machine Learning and Vision API. At Google, we work with a wide range of customers, from startups and companies beginning to explore the public cloud, to large financial institutions and retailers, to emerging industry leaders like Spotify. When it comes to data and analytics, we see 4 common use cases. Our customers are usually looking for storage solutions, for databases for the new and existing applications that they're moving to the cloud. They may be looking for big data platforms that can scale with their business, or for technologies to make their applications more intelligent. Let's look at each of them in turn. Let's start with storage. Google Cloud Storage, or GCS, offers developers and IT organizations durable and highly available object and file storage. GCS is ideal for backups, archives, and images for your web applications. It is also commonly used for big data applications for both staging and permanent storage. GCS is very cost-effective with a pay-for-what-you-use model. It's also very secure with all data encrypted by default and very reliable with automatic replication across multiple regions. Google Cloud Storage offers 3 classes of service to better meet your needs: standard, durable reduced availability, and nearline. Nearline is a fantastic choice for cold data storage, such as data stored for legal or regulatory reasons. Nearline offers a unique combination of low cost and low latency. It is priced at only 1 cent per gigabyte per month and allows you to retrieve your data in just a few seconds. Let's now talk about cloud databases. Google Cloud Platform gives you a few choices to run your applications: Compute Engine, to run your workloads on virtual machines; App Engine, which is a platform for scalable web apps and mobile backends; and Container Engine, which allows you to run Docker containers on Google's infrastructure. They are all great choices with support for many different programming languages. Now, a key question is, after choosing where you want to run your apps, where should you store your data? Google Cloud Platform gives you several options so that you can pick the right data stores for your applications. As I mentioned, Google Cloud Storage is a great choice for your files and your binary data. When you're looking for a relational database, we offer Cloud SQL, a fully managed MySQL service. It's high performance, highly available, and we take care of all the infrastructure details for you. Of course, it's fully compatible with any application that uses MySQL. For applications that need a NoSQL database with flexible schemas, horizontal scalability, and high throughput, we offer Cloud Data Store, a document-oriented database that is a great alternative to MongoDB. We also offer Cloud Bigtable, a managed HBase database service. Finally, we offer a high-performance and scalable Memcache key value store, which is ideal for web and mobile apps, as well as for caching user sessions. In addition to these products, we also offer a wide array of open source and commercial databases through the Google Cloud Launcher, which allows you to deploy new database instances or clusters in just a few clicks. That's a great choice if you would like to use products such as Postgres, MongoDB, Cassandra, SQL Server, or Redis. Let's now talk about the third use case, which is big data. Big data is, of course, one of the most talked about technologies in the industry today. It is at the top of the agenda for most IT organizations, and it's increasingly becoming a key area of differentiation. There are many applications for big data technologies, from marketing analytics to fraud detection, mobile gaming to Internet of Things, from genomics to scientific research. Big data is at the core of many things we do at Google, so it's no surprise that we offer a comprehensive set of products to help our customers. The best way to think about big data is to look at the life cycle of data. The initial stage is data capture. We offer several products depending on your use case. You may have logs or monitoring metrics that you want to analyze. You may have web and advertising data from Google Analytics, data from your legacy applications, etc. We make it very easy to get data from any source through a variety of connectors. If your data is being streamed in real time, you can use Cloud PubSub, a cloud-native, fully managed service. One of the unique things about PubSub is its operational model. All you really have to do is create a topic and send events. That's it. No need to provision capacity, manage a system, or worry about availability. This is in fact a common theme across many of our services. After you capture your data, you can process it with Cloud Data Flow. It's also a fully managed service using an open source programming model, which we recently released as Apache Beam. Apache Beam and Cloud Data Flow support both batch and stream models. And just like PubSub, you don't need to manage any infrastructure. They just scale. Now, after processing your data, you can store it in Google Cloud Storage or any of the database that I mentioned earlier. Or you can put it into BigQuery, our cloud data warehouse. You don't have a choice of fully managed services to analyze your data. You can use BigQuery for high-performance SQL queries. Again, absolutely no need to manage. Just load your data and start querying. As some of our customers say, it's truly magical. Now, for programmatic analytics, you can use Cloud Data Flow, which works in batch and stream mode. Or if you want to use Spark or Hadoop, you can use Dataproc, a managed service that allows you to deploy a cluster of dozens, hundreds, or even thousands of nodes in under 90 seconds. Dataproc truly brings the benefits of cloud computing to Hadoop and Spark. Ultimately, you want your users to benefit from all your data and analytics. Many of our partners offer tools that integrate with Google Cloud Platform, such as Tableau, Qlik, and iCharts. We also just announced a new Google product targeted at business users. Data Studio is one of the core components of the new Google Analytics 360 suite. It allows business users to easily create reports and dashboards and analyze their data in BigQuery and other Google products such as Google Analytics. It works just like Google Apps, making it easy to share and collaborate with other users. For data scientists and developers who want to explore data, we offer Cloud Data Lab. It is an interactive environment based on the popular open source IPython and Jupyter projects. Data Lab makes it very easy for data scientists to query data stored in BigQuery or other data sources, create machine learning models, visualize their data, and share their notebooks with their colleagues. So with Data Studio for business users and Data Lab for data scientists, we offer two great options for data visualization and exploration that complement our partner ecosystem. That takes us to the fourth use case, machine learning. At Google, we use machine learning extensively to power our applications. Machine learning enables image search on Google Photos, voice recognition, language translation, and even self-driving cars. Machine learning can now be used for a wide range of use cases across many industries. It can be used for classification, for example, predicting which customers are at risk of going to a competitor. It can be used for product recommendations, for content personalization, maybe to detect anomalies in financial transactions, manufacturing, or data center operations. Machine learning is also a powerful tool for getting intelligence out of unstructured data. For example, image recognition can help identify damaged shipments or identify which products are on the shelves of a supermarket. Also, text analytics can help analyze call center conversations or detect the topic and sentiment of any text. To make it easy for anyone to gain the benefits of machine learning, we introduced TensorFlow last year. TensorFlow is an open source project that makes our deep learning technology available for any applications. This is a technology that powers over 100 Google services. It can be used for many classes of applications, including vision, speech, text, video, financial modeling, and more. Since we released TensorFlow, we've gotten an incredible response from the community. TensorFlow is now the most popular machine learning project on GitHub. TensorFlow is designed for portability and runs on a wide range of platforms, including, of course, Google Cloud Platform. We're very excited to announce today our new cloud machine learning product family, or CloudML for short. CloudML is a family of products that takes machine learning from research to production. It has a rich training capability with API compatibility with TensorFlow. CloudML is integrated with the rest of our powerful tools like Cloud PubSub, Cloud Data Flow, BigQuery, and Cloud Data Lab to make the experience of getting a model trained much simpler. CloudML is fully managed, so the only thing you have to think about is your model. We'll worry about the CPUs, memory, network, disk, and runtimes. Our new CloudML product family also includes a set of application-specific APIs that allow you to build intelligence into your applications. Our Cloud Vision API does an amazing job of enabling applications to understand images. A developer just needs to point the Vision API at an image through a simple API call, tell us what they would like to know, and we can then use the power of a fully trained Google model to quickly analyze what's there. The Cloud Vision API can detect objects in an image, faces, landmarks, logos, and improper content. It can also automatically recognize text. We've been very happy with all the creativity shown by developers who have been using it since we launched the alpha in December. As you've heard in the GCP Next keynote, we also have other machine learning APIs like Translate and Speech. I can't wait to see all the amazing applications our customers will build over the next few months. This gives you an overview of the key components of the Google Cloud Data Platform. We talked about storage, databases, big data, and machine learning. We also talked about some of the key reasons that make Google a great choice for your data and analytics. We offer fully managed services so you don't have to worry about operations or infrastructure. We give you a full set of databases to meet the needs of your applications. With the new CloudML product family, we can help you make all your applications intelligent. And finally, we make it easy for all your users to understand your data and make better decisions. Thank you very much for your time, and I look forward to seeing what you will accomplish with Google Cloud Platform.
Well, that's it for us here at GCP Next 2016, and it's been an awesome couple of days.
I hope you enjoy the inside look you got at the conference and a chance to see the buzz that's happening here.
We'll hope you join us next year, either in person, we'd love to have you, or join us again online on the live stream.
Can't wait to see what you build next.